We are now ready to prove that a graph G is bipartite if and only if it contains no odd cycle. In order to prove this, we have two things that we have to do. First, we have to show that if the graph is bipartite, then it has no odd cycle. Next, we'll have to show that if it has no odd cycle, then it is bipartite. So let's start with the first direction, this direction, which is showing that if G is bipartite, then G has no odd cycle. Odd cycle. This is what we aim to prove right now. So what we do is we suppose that G is bipartite. Suppose G is bipartite. Bipartite. And you should really remember that then what bipartite means. It means that the vertex set of G can be written in two partitions. So basically, the entire vertex set is either in X or in Y, and they do not overlap. This just means that no vertex of X is also a vertex of Y. They do not overlap. Their intersection is empty. And for every edge, in the graph G, the edge is of the form xy, where x is in the set X and Y is in the set Y. So in other words, a graph is bipartite means that its vertex set can be partitioned into two vertex sets, X and Y, that don't overlap, so that every edge in the graph goes between those two partite sets. Alright, so that's what we know. The graph is bipartite, and we want to show that it has no odd cycle. So we can actually do this by contradiction. What we will do is we want to show there's no odd cycle. So suppose G has at least one odd cycle. So we only need to suppose it has one odd cycle in order to show that this won't work, but it could have more. We're going to have a contradiction in this case. So what we're going to do is we're going to suppose that it has an odd cycle and then show that this is impossible. Alright, so it has an odd cycle, and let C be an odd cycle, so it's vertex 1, v2, all the way up to vn, where n is odd. Be an odd cycle in G. Okay, so now what we can do is basically the same idea as the coloring technique that we did before. We can just say we're going to let v1 be part of the set X, and then v2 will have to be part of the partite set Y, because there is an edge v1 to v2, so if v1 is in X, then v2 has to be in Y. Now it's arbitrary that I said v1 could be in X. You could also have said v1 in Y and run the exact same argument. Doesn't matter. But what this tells us is that in general, vi will be in either X or Y, depending on if I is odd or if I is even. But now that means that Vn is going to be in X because n is odd. Right up here we know that n is odd. Well, we know now that V1 and Vn are in X, but V1, Vn is an edge of the graph, and we already know that the graph is bipartite. So this right here is a contradiction. And when you come to a contradiction, you normally write this. It means that there is an error. This is impossible, which means that what we've supposed here, that the graph has at least one odd cycle, is impossible. We conclude then that therefore G has no odd cycles. So we have just seen that if G is bipartite, then it has no odd cycles. So let's go back up to the main thing that we're trying to show. We're trying to show that a graph is bipartite if and only if it contains no odd cycle. And we just showed one direction. So now we have to go ahead and show that if it has no odd cycles, then it is bipartite. So let's write this portion using purple. So we're going to do this part. We want to show that no odd cycles implies bipartite. So we go ahead and we say, suppose that all cycles in G have even length. So we suppose they all have even length, and we want to show then that G is in fact bipartite. And now it's kind of important to notice that we didn't specify that G is connected. So if G is disconnected, if G is disconnected, then any cycle in G is contained in one of the connected components. One of the connected components. So for example, if G consists of like a bunch of different components like this, maybe this is going to be a component G1 and G2 and G3, and maybe there's a bunch of them. All of these components are connected. Well, then any cycle in the whole graph has to be contained in one of these guys. So there's some cycle and there's another cycle. But each cycle has to be within one of the connected components. And so then what you would have to do is you would have to just show that if each one of these is in fact bipartite, so you can split this into x1 and y1, and you can split these vertices into x2 and y2, so you show this is bipartite, you show this is bipartite, and you keep doing that. Then for the whole graph, all you do is you say, well, your partite set X is all of the xi's. So it's x1 union x2, and you keep going to the end, union x, I don't know how many components you have, maybe let's say we have k components. Then that's all you do. You just take the two partite sets to be that. y1 union y2 all the way up to yk. So in other words, if the graph is disconnected, then you just look at each of its connected components and you try to show that that connected component is bipartite. And then you will have completed the proof for the entire graph. In other words, it suffices to show that if there are no odd cycles in a connected component, then it's bipartite. So what we need to do is just take a look at things that are connected. So it suffices to show the claim for connected graphs. So we assume G is connected. Once we've showed the claim works for connected graphs, then if the graph was disconnected, you just run the claim through all of the connected components and you're done. Alright, so now comes the important part of the proof. Basically what we know is that all of the cycles in G have even length. And what we want to do is we want to define the partite sets of the graph. So what we'll do is we'll say, let V be a vertex of the graph. And it's pretty much arbitrary. You just choose a vertex. Then what you do is you define two partite sets, x and y. And you'll define the first set to be all vertices in the graph which have distance in the graph from vertex V being an even number. So let's just say is even. So if you take a particular vertex v, and then you go ahead and you find all of its neighbors, those neighbors would have odd distance, and then if you look one further away where they have even distance, you're going to have it belong to the set X. So let's just do this. V and Y have odd distance. Alright, so now you've split up the vertices. Since G is connected, we know that X together with Y is going to cover all of the vertices. Why is this? Well, if you look at any vertex in the graph, it will have to either have even distance or odd distance from the vertex that we've chosen, vertex V. And that's because the graph is connected. So there will be a path that goes from that particular vertex to our vertex V. Okay, so that just means that you've covered all of the vertices, and that holds. Now, why is it true that X intersect Y is empty? Well, it's impossible for there to be a vertex in the graph which has distance both even and odd, because the distance between two vertices is the minimum length of a path. So if there is a path of minimum length 2 and a path of minimum length 3, well, that doesn't make sense because the minimum length is in fact 2, not 3. 3 is bigger. So it just holds that you cannot have the distance between V and any other vertex be both even and odd, so that's why they don't intersect. Alright, so now we know that G is connected and we've sort of partitioned up the vertex set in this way, so what we need to show that any edge in the graph is of the form x, y, where x is in x and y is in y. In other words, we need to show that having x, y being an edge where x and y both belong to x, or x, y both belong to y is impossible. That's what we want to show. We want to show that every edge is of this type. In other words, there are no edges that go between vertices in set X or between vertices in the set Y. So let's go ahead and do that. And the proof will be the same for X and Y both in X or for X and Y both in Y. So let's just go ahead and say, let X and Y both belong to the set X. Okay, so our goal here is to show that xy is not an edge. Goal is to show xy is not an edge, right? Because we don't want edges like that. So anytime we have x and y both belonging to the set X, there should not be an edge between them. That's what we want to show. What we do is we let P from V to X be a shortest path from V to X. So V was our original vertex that we chose. We chose V so that every other vertex was partitioned into two partite sets depending on if its distance from V was even or odd. That's the vertex V that we're talking about. So we're now going to let P be a shortest path from V to X. So here we have V, over here we have X, and over here we have Y. And we have some path P from V to X, and it's going to be shortest. There might be more than one, so we just take one of these. And also, Q is going to be from V to Y. And again, I'm putting a star here because I don't know the actual length of what it is, but it's going to be a shortest path from V to Y. Okay, in fact, we should point out that these will have to have the same parity because both of these x and y belong to the same partite set. In fact, we said they both belong to x. That means that the path P that goes from V to X must be of even length, and similarly, the path from V to Y must be of even length. The important part is they have the same parity. So since X and Y both belong to the set X, P and Q are both of the same parity. In fact, we know that the same parity in this case is even. If you run the proof again where X and Y are both belong to the set Y, then you'll see that they're both odd, but again, this holds that they're of the same parity. Same parity means they're both even or both odd. Now I'm going to draw the path P in pink over here, and so the path P goes over to X, and in fact, the path Q definitely shares a vertex with the path P. In particular, it shares the vertex V, but it may even share other vertices. It may intersect at other places, and what we want to do is let W be the last place where it intersects. So through here it might intersect and touch each other a little bit, but after that you want it to not touch ever again. So let W be the last common vertex of P and Q. We know that there is a common vertex of P and Q, in particular V is common. And if there are no others, then V is W. But we want to let W be the very, very last one that they have in common. Okay, and now we're going to let this portion of P up here be called P1, and this portion of Q down here be called Q1. And over here, similarly, we'll call this portion of P, the remaining bit that goes from W to X, P2, and the remaining bit of Q down here is Q2. So what we have is P1 goes from V to W, and P2 goes from W to X, so that P is, in fact, P1 followed by P2. We can actually write that this is equal to that. And similarly with the Q path, we know that Q1 goes from V to W, and Q2 goes from W to Y, where Q is simply Q1 followed by Q2. So this is sort of what we've done. We've just said, okay, W is the last place where they have something in common, and then we'll just label each of these four pieces of path separately so that we can make particular arguments about these paths. Now, since P is the shortest path, or a shortest path, from V to X, and also Q is a shortest path from V all the way over to Y, we know now that P1 and Q1 should have the same size, because if they don't have the same length, then what would happen? Well, there's a particular way to get from V over to W, and if you could do it in a faster way through this green path, then why wouldn't you have done that? You would have done that to get to X in a shorter way. So since P and Q, well, it shouldn't look like a P1. Since P and Q are shortest, it follows that the length of the path P1 is equal to the length of the path Q1. Just think about that for another minute to make sure that this makes sense. Because P and Q were taken to be shortest paths, then it follows that this piece right here and this piece right here have to have the same length. If they don't, then there's a shorter way to get through to one of the paths. Right, so now we know that P and Q have the same parity, so the full length of P and Q have the same parity, and also we know that these first pieces, P1 and Q1, have the same length. So what that means is, if you take those two pieces together, you now know that then I should start with P, P2 and the length of Q2 have the same parity. Same parity. in particular, in this case, because x and y both belong to x, we know that the full length p1, p2, that's the path p, has an even length, and then we remove a piece of a particular length k. Similarly, the path q that takes q1 to q2 has an even length, and we remove a portion that also has length k. So whatever we're left with is even minus k over here, and similarly it'll be even minus k. So it will have the same parity. P2 and Q2. Alright, this piece and this piece. So they have the same parity, which means they're both even or they're both odd. But now what that means is if you look at the path, I'll draw in red, the path that goes from x to w using P2, but sort of going in the reverse direction, and then continuing down Q2, we know that this has either an even or odd, but in total it will be even. So then the path that goes from x to w using P2 and then using Q2 to get to y. And actually we're not really using P2 in this direction, we're using it in the reverse direction. So when we reverse direction, we usually write an inverse like that to mean that we're traveling the path in the other way. So this path has even length. This red path here should have even length. So go through this carefully and make sure that it's fully understandable. You have to be able to see that this red path here must have even length. Now, what's the big point that we're trying to make? We are trying to say that since x and y belong to the same partite set x, in this case, we want to show that this edge is impossible to have, this edge xy. And we're almost there. Because what we do is we say, now, if xy is an edge of the graph, then if we take the path P2 inverse followed by Q2 and then together with this final edge, together with the edge xy, that whole thing will form a cycle of odd length. We should be careful. It will have odd length because this piece in red has even length, and we've just, let's just view it again. This piece in red over here has even length, and if you have this as an edge, then this forms an odd length cycle. And what do we know about the graph? Well, we know that every cycle in the graph is, let's go back to the very beginning, every cycle of the graph has even length. That's where we started with. So if every graph in the cycle has even length, we can go through this whole process and show that in fact then this edge here, any edge between two vertices in the same partite set, cannot be an edge, right? If it is an edge, then we've just formed a cycle of odd length where we know that is impossible. So xy is not an edge of the graph, where we took x and y to be from the partite set x. So exactly the same proof. We do the same holds if x and y are both from the partite set y. We'll then be able to show that xy is not an edge of the graph. So you should be able to do this using the exact same argument. In fact, nothing changes in the argument at all. The only difference was that up here, when you take the path P and Q to be shortest paths from V to X and from V to Y, we will know that those paths P and Q will both have odd length, but that doesn't matter. What you're using is the fact that they have the same parity. So literally the exact same proof will work if X and Y were both belonging to the set Y. Alright, so let's recap. What did we do? We said that if we have all the cycles in the graph being even length, we can consider simply the connected graphs, and then once we do that, we are able to partition the set of vertices into these two pieces so that it has all of the desired properties. This part, first of all, is obvious. We were able to see that it satisfies that condition. And the more difficult condition, the fact that the only edges can go between x and y, as partite sets, that was a little bit harder to show, but we used the fact that all of the cycles had even length in order to show that part. So that's what we did down here. And thus, we conclude that a graph is bipartite if and only if it has no odd cycles.